Okay, Assalamualaikum warahmatullahi wabarakatuh. Last time we have learned about um, the formula for energy balance for an open system, and then we know that this is the formula that we had after we derived from the net energy, where the total of energy input and output, also after we consider work and heat in the system. So what we have here is the net rate at which E is transferred to the system as heat and or shaft work Q plus WS equals the difference between the rates at which the quantity is transported into and out of the system, which is delta H, delta EK, and delta EP. That's why we have this formula. Okay, now we proceed to the next part. Okay, let's see this part. Okay, if we have this equation, then try to solve for each case. Okay, if there are no moving parts in the system, means Ws equals 0, where from this formula we can omit this part. Okay, and if the system and its surrounding are at the same temperature, means no heat transfer, so Q equals 0. If the linear velocity of all streams are the same, where that velocity we can relate to kinetic energy formula, which is half mv squared, then delta EK will be 0. Last but not least, if all stream enter and leave process at a single height where no elevation occur, so we have delta EP equals 0. Okay, now let's have a look at this example, the turbine energy balance. We have the mass flow rate of turbine 500 kg per hour. Steam enters at 44 atm. The pressure of the inlet, okay, and also the temperature for the inlet is 450 degrees C at 60 meter per second, where this is the initial velocity, and leave a point 5 meter below the turbine inlet at atmospheric pressure with a velocity of 360 meter per second. So this will be the outlet velocity. And also we know that initially it is at the ground level and later on it leaves 5 meter below the turbine inlet. Okay, next we have the shaft work value of 70 kilowatt, and the question said the turbine delivers a work, means the turbine did a work to the surrounding, okay, or work done by the system. So the sign will be negative, right? Because the work is done by the system to the surrounding, and heat loss is estimated at 10,000 kilocalorie per hour. So heat loss means negative Q. Then we need to find the specific enthalpy change, or in other words, we need to find delta H per M, because we have specific term here. As we learned before, if we have specific, means we need to divide the value that we have with the total amount of the mass or mass flow rate for the system. Okay, let's have a look at the solution. Okay, if we draw a flow chart, we know that this is the mass flow rate, this is the inlet condition, this is the elevation of the system, where we have a negative 5 meter because it moved below the inlet of the turbine. And then we have the outlet condition. Okay, also we have negative 10 to the power 4 kilocalorie per hour, where heat loss, and also we have negative 70 kilowatt because work done by the system to the surrounding. Okay, so if we use the formula that we have derived before, the energy balance for an open system, okay, this is after we rearrange the formula. Okay, previously we have delta H plus with delta EK plus with delta EP. Okay, and then for this part, since we have minus work done by the system to the surrounding. That's why we have this negative sign. Also, we put the formula for kinetic energy and also the formula for potential energy, and bear in mind we need to use m squared, and then we factorize u2 squared minus u1 squared, because this is the outlet velocity, this is the inlet velocity. Okay, and then also for this one, this is the outlet height, this is the inlet height, the initial height. Okay, so if we plug in the value that we have, where we have 10 negative 10 to the power 4 kilocalorie per hour, then we have minus 70 kilowatt, we have half m 500 kg per hour, also v outlet squared minus v inlet squared, where we have the outlet velocity equals 360 meter per second, and we have the inlet velocity as 60 meter per second. And then this is the formula for potential energy, where we have mass flow rate, we have the gravitational acceleration, also we have the elevation here. So if you find the value, you will get this value. But before you can get this value, you need to use this relationship where 1 kilocalorie equals 4.148 kilojoule, because here we have kilocalorie, and then we want to find the value in kilojoule. That's why we need to convert this value first, and then later on for this part we don't have to do anything, because kilowatt means kilojoule per second. Okay, and then here you need to convert the unit, because this is in kilogram per hour, so you need to convert it become kg per second, because this is second per second in SI unit. The same goes here, you need to convert kg per second, and then after you convert the formula, you will get this value. Okay, try to do it, and if you have any problem, please let me know. Okay, now let's proceed to the next subtopic, where we have reference state and state properties. Okay, it is not possible the absolute value of the specific internal energy or the specific enthalpy. Okay, so we need to find the change in specific property. Okay, to permit quantification of the difference between various states, it is convenient to define a reference state and to list changes from this state for a series of other states. Normal reference state, the most stable physical form of the same substance at a specified T and P of 1 bar or 1 atm. However, any non-normal condition could be chosen as a reference state. Later on, we will look what is the meaning of reference state here, given here. Okay, then we have state property or property of a system, such as specific enthalpy, specific internal energy, depends on the state of the system, the temperature, the pressure, phase, and also the composition. Okay, for example, if we have this carbon monoxide, the phase is in gas phase, and the temperature is 0 degrees C, the pressure is 1 atm, and then we want to, and it is converted to carbon monoxide at 100 degrees C, but at the same pressure. So the change in enthalpy will be 2919 joule per mole, and then this is after we change to 500 degrees C at the same pressure condition, also the same state. The value will be 15,060 joule per mole. How do we get this value? We need to refer to this table, where at 0 degrees C, and also at 0 degrees C it will give 0 joule per mole. So this will be the reference state for this system. Okay, that's why if we find the change, the enthalpy change from 0 to 100, we need to look at this value, where 0 to 100, and then we know that this is the value at 100 degrees C, 2919, and then the value at 0 degrees is 0 joule per mole, That's why we have 2919 minus with 0, we get 2919 joule per mole. The same goes here. If we look at 500 degrees C, and then the reference state is at 0 degrees C, so we take this value 15,060 minus with 0. That's why we got this value 15,060 joule per mole. This is very easy. The most important thing is to determine which value will be the reference state for this system. In other words, since we have used the reference state here, we will get delta H 12919 joule per mole, where it is not an absolute value. And then the same goes to 500 degrees C, because we use reference state at 0 degrees C. Okay, now we proceed to the next part. We have a data table for saturated chloromethane, okay, where the state is liquid, vapor, vapor. At -40 it is in liquid form, the pressure is 6.878, and the specific volume is 0.01553, and the enthalpy is 0. Okay, look at other value, okay, at other conditions. Okay, so the question is, what reference state was used to generate these values? The answer is the state at which enthalpy equals 0. Okay, because if we use at enthalpy equals 0, we can get delta enthalpy easily, because we just minus 196.23 with 0, we can get the specific enthalpy from -40 to 0 degree Fahrenheit. The same goes to -40 degree Fahrenheit goes to 50 degree Fahrenheit, where we will use 202.28 minus with 0, we will get 202.28 BTU per pound. Okay, this is to explain the information where it mentions that, however, any non-normal condition could be chosen as a reference state. Okay, not necessarily we choose 0 degrees C, 1 bar. Okay, like for this case, we use -40 degree Fahrenheit as the reference state. Okay, next, we need to calculate the enthalpy change and also the internal energy change for the transition of saturated chloromethane vapor from 50 to 0 degree Fahrenheit. So we need to refer to this point and also this point, because the question asks us to find the value of delta H and also delta U from 50 to 0 degrees C. So we just ignore this part, the upper part, because this is at -40 degree Fahrenheit. If you look at the solution, where we have delta H equals H at 0 degree Fahrenheit, because this is the final state, minus H at 50 degree Fahrenheit, this is the initial state, where we refer the table here. Okay, this is the value at 50 degree Fahrenheit, we have 202, at 0 we have 196, then the initial state is at 50 degree Fahrenheit, where we need to take the final state minus the initial state. That's why we take 196.23 minus with 202.28 as shown in the solution here. Then we get -6.05. Then we go to the internal energy formula that we have learned before, where we have delta U equals delta H minus delta PV, where delta H we already obtained here, okay, from this part. Then P2 V2 minus P1 V1, where it is can be obtained from the table. Okay, the value of P and V from the table here. Okay, 18.9 psi for 0 degree Fahrenheit. Also, the specific volume at 0 degree Fahrenheit is 4.969. Then this is for 50 degree Fahrenheit, the value of pressure, so the value for specific volume. So we go back to the solution. Okay, that's why we have 18.9 times with 4.969 minus with 51.99 times with 1.920. Then we need to convert the unit. Okay, then if you convert the unit, you will get this value, -4.96 BTU per pound.